Organic retrosynthetic analysis is a foundational strategy in modern synthetic chemistry, enabling the rational design of complex molecules from simple, commercially available precursors. First formalized by Elias James Corey in The Logic of Chemical Synthesis, retrosynthesis has evolved into both an intellectual framework and a practical tool that underpins advances in pharmaceuticals, materials, science, and fine chemicals. Concept and philosophy of retrosynthesis. Retrosynthesis is a problem-solving approach in which a target molecule, TM, is systematically deconstructed into simpler structures by working backwards. This reverse logic contrasts with forward synthesis, where one builds molecules stepwise from starting materials. The central question guiding retrosynthesis is, what immediate precursor could give rise to this molecule in a single forward step? Through iterative application of this reasoning, the target molecule is reduced to simple, accessible starting materials, generating a retrosynthetic tree that maps multiple possible synthetic routes. Key terminologies in retrosynthesis. Synthons. A synthon is an idealized fragment derived from the disconnection of a bond in the target molecule. Synthons are often conceptual and may carry formal charges to indicate their reactivity. Example: disconnection of a secondary alcohol. Here, the carbocation and hydroxide are synthons. Synthons do not necessarily correspond to real reagents. Instead, they guide synthetic planning. Synthetic equivalents. Synthetic equivalents are the actual reagents used in the laboratory that mimic the reactivity of synthons. Example: synthon, R2C+. Synthetic equivalent: ketone, such as acetone. Synthon, alkyl anion or carbanion. Synthetic equivalent: Grignard reagent, RMGX. Thus, synthons translate conceptual disconnections into experimentally viable transformations. Functional group interconversion, FGI. FGI refers to the transformation of one functional group into another to enable a more strategic disconnection. Examples: alcohol to ketone, oxidation; alkene to alcohol, hydration. FGI is frequently employed to convert a molecule into a disconnection-friendly form. Functional group addition, FGA. FGA is the introduction of a functional group into an otherwise unreactive framework, typically replacing a hydrogen atom. Purpose: to create a reactive site for disconnection. Example: alkane to alkyl halide, via halogenation. Enables subsequent nucleophilic substitution or elimination. FGA is essentially the reverse of functional group removal, for example, hydrogenolysis. Target molecule, TM. The target molecule is the compound of interest whose synthesis is being designed. Retrosynthetic analysis begins with the TM and proceeds backward. Core operations in retrosynthesis. Disconnection. Disconnection is the conceptual cleavage of a bond in the TM to generate synthons. It is represented by a retrosynthetic arrow. Strategic disconnections reduce molecular complexity. Often, target bonds are formed via known, reliable reactions, for example, carbon-carbon bond formation. Transform, TM. A transform, TM, refers to a recognized reaction pattern applied in reverse during retrosynthesis. Example: aldol reaction to beta-hydroxycarbonyl formation. Retrosynthetically, beta-hydroxycarbonyl can be formed from an aldehyde plus an enolate. Transforms are essential in mapping backward steps to known forward reactions. Functional group addition or removal patterns. Strategic addition or removal of functional groups FGA or FGI, enables access to canonical disconnection patterns such as 1. 2 disconnections for vicinal diols or olefins, 1. 3 disconnections for carbonyl compounds, 1. 4 disconnections for Michael acceptors. Strategic principles of retrosynthetic analysis. Simplification. Each disconnection should significantly reduce molecular complexity. Fewer rings, stereocenters, and functional groups. Convergence versus linearity. Linear synthesis, sequential stepwise construction. Convergent synthesis, independent preparation of fragments followed by coupling. Convergent strategies are preferred due to improved overall yield and efficiency. Strategic bond selection. Key bonds for disconnection include bonds adjacent to functional groups, bonds formed via reliable reactions, for example, C-C coupling, nucleophilic addition. Minimization of protecting groups. Protecting groups complicate synthesis and reduce efficiency. Their use should be minimized unless necessary. Exploitation of symmetry. Symmetry simplifies retrosynthesis by reducing the number of unique intermediates and enabling convergent strategies. Illustrative example of retrosynthetic disconnection strategy. In 2020, Professor Richmond Sarpong's group at University of California, Berkeley published an article titled Retrosynthetic Strategies and Their Impact on Synthesis of Arcutane Natural Products. In that article, the authors proposed that functional group and transform-oriented retrosynthetic approach complements topology-driven analysis by prioritizing existing or latent functional groups as guides for strategic bond disconnections. In contrast to skeleton-based methods, this strategy is inherently subjective, reflecting the broad range of possible synthetic pathways. A key element is the identification of retrons, structural motifs such as 6-membered rings that imply specific transformations. In arcutane natural products, heteroatom-containing functional groups are predominantly located at the periphery. However, the core structure still supports a variety of functional group-directed disconnections. For instance, a 2-2-2 bicyclic framework may be traced back to a Diels-Alder reaction, though this requires incorporation of a double bond within the bicyclic core, often necessitating additional steps to adjust oxidation states. Although exhaustive enumeration of functional group-based transformations can produce numerous impractical routes, integrating this strategy with bond network analysis enhances retrosynthetic efficiency and flexibility, and can facilitate the discovery of new synthetic transformations. Retrosynthetic analysis of prostaglandins. A recent retrosynthetic study of prostaglandins, reported in Nature Communications, outlines a hybrid strategy integrating both polar and radical disconnections. The cis-olefins are introduced via the classical Wittig reaction, while the trans-olefin side chains are constructed through a nickel-catalyzed reductive coupling, representing a radical-based transformation. This approach identifies a bromohydrin intermediate as a radical analog of the corylactone. The bromohydrin can be readily synthesized from a chiral lactone using N-bromosuccinimide in aqueous conditions. Two routes were proposed for the preparation of the chiral lactone. The first involves an enantiomer divergent in vivo Baeyer-Villiger oxidation, enabling direct lactone formation in a single step. However, this biotransformation is less practical for conventional synthetic or medicinal chemistry laboratories. An alternative and more accessible route employs commercially available lipases to generate the chiral intermediate, followed by a Johnson-Clayson rearrangement to furnish the lactone. Based on this analysis, the corylactone equivalent can be synthesized efficiently in only 2 steps. Retrosynthetic trees and root optimization. A retrosynthetic tree maps multiple disconnection pathways. Chemists evaluate these roots based on step count, yield, cost, and availability of reagents, chemoselectivity, and regioselectivity. The optimal route balances efficiency, feasibility, and practicality. Computer-assisted retrosynthesis. Recent advances have transformed retrosynthesis through computational tools such as Cynthia, formerly Chematica, developed and commercialized by Millipore Sigma. Key features: database of more than 100,000 expert-coded reaction rules, automated application of transforms to generate precursors, evaluation via scoring functions, chemical scoring function, CSF, measures structural simplification, reaction scoring function, RSF, evaluates feasibility, step count, and compatibility. Workflow: identify possible disconnections, apply reaction rules to generate precursors, evaluate precursor availability, and iterate until simple starting materials are reached. Finally, rank synthetic routes based on efficiency and feasibility. Advantages: rapid exploration of vast chemical space, identification of non-intuitive synthetic routes, and reduction of human bias. Limitations: may undervalue long-term strategic planning, requires accurate reaction rules and datasets, less effective for highly novel or unprecedented transformations. In conclusion, retrosynthetic analysis remains an indispensable tool in organic chemistry, integrating conceptual reasoning with practical laboratory constraints. By employing key concepts such as synthons, synthetic equivalents, FGI, FGA, and strategic disconnections, chemists can design efficient synthetic routes to complex molecules. The emergence of computer-assisted tools like Cynthia further enhances this process by combining chemical intuition with algorithmic power, marking a significant step toward the future of automated synthesis design.